We'll continue our lesson with the second part of chapter 3. This time is about ionization energy. First of all, let's see the learning outcome. After finish this lesson, you should be able to explain and use the term ionization energy and the factors influencing the ionization energies of elements. Then you can use ionization data to explain the trends across a period and down the group of the periodic table. Reduce the electronic configurations of elements. And then you should be able to interpret successive ionization energy data of an element with the periodic table. We continue with the definition. What actually is ionization energy? Ionization energy is the energy required for an atom of an element to release the outer electron to become a positive ion. The successive ionization energy, the first is the energy that the atom needs to release one electron from a neutral atom to form a positive one ion. Then here you have the first ionization energy. For example, when you have Mg as an atom, when this release one electron, as you know, magnesium number 12, so the electronic configuration is 1s2, 2s2, 2p6, 3s2. Here, the outer shell is 3. There are 2 electrons. When one of these 2 electrons in this 3s want to be released, only one, then the Mg become Mg plus. Neutral, here neutral. 1 minus 1 plus. After Mg become Mg plus, then still can release one new electron. So from Mg plus, release one electron to form Mg2 plus. In this case, then the electron release this time is the second one from this. So the energy needed is second ionization energy. If the atom want to release one electron from here, then become the third. So the energy is the third ionization energy. So once again, the first ionization energy of an element is the amount of energy required to remove one electron from each atom in 1 mole of gaseous atoms, producing 1 mole of gaseous cations. Once again, here there is the equation. The first one, this one is the first ionization energy. because from atom neutral to B plus 1 and release 1 electron. The second one here, the second ionization energy to release the second one electron from the X plus 1 ion, and the result is plus 2 ion. That's the second, and then the third here to form plus 3 ion, release the third electron. That's the third ionization energy. If we get the sum here, so all of here we have 3 electron release. That's what we mean as successive ionization energy. The ionization energy is affected by 3 factors. The first is the size of the nuclear charge. The second factor is the size of the atom or ion. Atom for the first, ion for the next, the second or the third or the fourth. The third factor is the screening or shielding effect. Then here, as the global pattern, you should know here the trend of ionization energy down a group decreases and across a period increases. Why is that? We can continue our discussion. Here we have periodic table and we have the successive, not successive, sorry. Here we have the first ionization energy value. We have hydrogen here. We check hydrogen is in group 1 here. And then you have helium. Helium in group 18 or noble gas, group 8A. Then you have lithium. Please check here. Lithium, beryllium, boron, carbon, neon, oxygen, fluorine, and neon. Here are elements in the same period here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So there are in one period. In one period, the atom, all these atoms have two shells of atom. So the distance almost the same. And then you can check here the value. Lithium, beryllium, boron, carbon, neon, oxygen, fluorine, and neon here increases. Why increases? We'll explain using the 3 factors we mentioned previously. Then you have here from helium, this one, compare with lithium. Helium in period 1, lithium in period 2. So there is increase 1 shell, but the value drop here from helium to lithium. And then beryllium proton number 4, actually 4 proton, boron number 5 proton. So boron has bigger nuclear charge, but you can see here the value of boron, the energy is lower than beryllium. We have the explanation. Number 1 here. There is general increase in ionization energy across the period from lithium, the example, lithium until neon. Why? Generally increase because the nuclear charge increase. Nuclear charge caused by the number of proton. From left to the right, the number of proton increases. Then the distance between the nucleus and the outer shell electron remains reasonably constant. Why constant? Because in one period, the number of shell the same. Then the shielding by inner shell remain reasonably constant. So the shielding effect for the element in second period, so there are 2 shells. The shielding effect caused by the first shell electron. Fact number 2. There is a rapid decrease in ionization energy between the last element in one period, helium, in the example I explained before, and the first element in the next period, lithium. So you have helium here, period 1, and you have period 2, periodic table here, lithium. The distance between the nucleus and the outer shell increases. Yeah. The distance of helium, only 1 shell. So the distance from the nucleus here as the core of atom here, nucleus, you have proton and neutron and electron here in the shell. For helium, there are 2 electrons in the first shell. For lithium in period 2, there are 2 shells. Here, the second shell. Here, 1 electron because lithium number 3. So the configuration is 2, 1. So 2 electrons in the first shell and 1 electron in the second shell. So the distance for helium only short here, for lithium farther. So the size is bigger. If the size bigger, then the attraction between the positive and the negatively charged electron decreases. And the third, the shielding by inner shell increases. No shielding effect for helium because the electron actually in the first shell. For the lithium, there is shielding effect from the 2 electrons in the first shell. These two factors outweigh the increased nuclear charge. Fact number 3. There is a slight decrease in ionization energy between beryllium and boron. Beryllium number 4. This is the proton number. Boron number 5. Beryllium 1s2 to s2. Boron 1s2 to s2 to be 1. So the first electron to come out in the first ionization energy for boron here, this one, in 2p orbital or subshell. For beryllium, in 2s. So here, the fifth electron of boron, this one, in 2p subshell is slightly farther away from the nucleus. Then the distance between the nucleus and the outer shell electron increases slightly. The shielding effect by inner shells increases slightly. These two factors outweigh the increased nuclear charge. Fact number 4. There is slight decrease in the first ionization energy between nitrogen and oxygen. Nitrogen, atomic number of proton number 7. The configuration is 1s2 simplified as helium, the 1s2, and then after 1s2 to s2, and then 2p3. So the number of electrons is 7. 2, 2, 3. 2s, the subshell 2s has one orbital, described in one square here, one box. 2p, subshell 2p has 3 orbitals, described as 3 boxes here. We have 7. So 2s, there are 2 electrons. 1, 2. 2p with 3 orbitals, there are 3 electrons. According to Hun, so the occupation starting from the single 1, 2, 3. For oxygen, almost the same, but here in 2p there are 4 electrons, so you have 2s2, 1, 2, 1, 2, 3, 4. So the last one here, the electron to be released for the first ionization energy comes from the orbital with 2 electrons. Then there will be a repulsion force that help this electron to come out from the orbital. So the energy needed will be less than this one for nitrogen, because in here there is no repulsion force. Okay, here first ionization of aluminum is lower than that of magnesium. The same case here as nitrogen and oxygen. Magnesium from 3s, aluminum from 3p. So for aluminum, slight further from the nucleus. Then here for this is similar to beryllium and boron. For this one, phosphor number 15, sulfur number 16, then neon 10 electron, 10 electron until 2p6, 1s2, 2s2, 2p6, and then continue with 3s2, 3s2, and then here 12, 12, and then the rest is 4. So here of it there are 3 boxes, 1, 2, 3, 4 here, 2 in px, the orbital px. There are 2 electrons. Then this is the case similar to nitrogen and oxygen. So for sulfur there is a repulsion force between the pair electron here, but for phosphor the last electron to be released for the ionization energy is the single or half-pill orbital. Then we continue. How about the pattern donor group? Donor group, let's say we have group 1A or group 1. Hydrogen, lithium, sodium, potassium, rubidium, and cesium. Here in period 1, only 1 shell. Here in period 2, 2 shells. So the number of shells increase, and the distance between the nucleus and the outer shell increase, of course, because the number of shell increases. And then the shielding effect, the shielding by complete inner shell increases, because the number of shell increases. So the shielding effect increases. There are more electrons in the inner shell. These two factors outweigh the increased nuclear charge. The nuclear charge here, hydrogen 1, lithium 3, sodium 11, potassium 19, rubidium 38, cesium 55. If the nuclear charge increases, then there is the stronger attraction force to the outer electron. But this factor actually outweighed by the distance and the shielding effect. We summarize. The first ionization energy of an element is the energy needed. So this is the process is endothermic, to remove 1 electron, because this is the first, from an atom, the neutral atom, in 1 mole of atoms of the element in the gaseous state to form +1 ion. The ionization energies needed to remove the first, second, third, fourth, etc. electrons from each atom or ion in a mole of gaseous atoms are called successive ionization energy. The magnitude of the ionization energy depends on these four factors. The first is the distance of the electron from the nucleus. The second is the number of positive charges in the nucleus, proton, the nuclear charge. And then the degree of shielding of outer electrons by inner electron shells. And then the last is the spin pair repulsion. The trend across a period and down the group can be explained in the four factors. Values of successive ionization energies of atoms provide evidence for their electronic configurations. Then you can check yourself once again. If you can answer this, then you already understand. Explain why the first ionization energy of boron B is lower than that of beryllium, although boron has higher nuclear charge. And then explain why the first ionization energy of oxygen is lower than that of nitrogen. Then I hope you can exercise yourself, practice by answering the question number 10, page 42 of the textbook of AS level chemistry. That's all for chapter 3. So we finish with chapter 3.